the agenda. Before moving on to the agenda, let me talk a little bit about the housekeeping rules. So this webinar is where we would like everyone to participate and engage. Please type all your questions throughout the sessions on the chat box. So at the end of all the sessions, we will have a 15 minutes of Q&A session. And I would encourage you to type and write all the questions. Please keep yourself on mute. Please keep your video off unless you are speaking. Ensure that your devices has sufficient battery and you have a notepad or notebook or pen with you if you want to write something. You can raise your hand if you need to. We can allow you to speak if we have time in the Q&A session, but we would prefer still having a questions asked the chat section, so we can take filter the questions and take the most important one. We only have 15 minutes for the question and answer session. We will share the feedback form with you right after the webinar, so please submit your feedback. It helps us improve the webinar series, helps us plan for the next event. Now with that, I'll move to the next part. So I will introduce the session chair. So I welcome first, I would introduce Dr. Priyantha Wijayatunga. Dr. Priyantha holds a degree in electrical engineering from Sri Lanka and a PhD in power economics from Imperial College London, where he was a paid scientific research fellow. He joined the Asian Development Bank in 2008 and was director of South Asia Energy Division before he was appointed as the chief of Energy Sector Group in August of 2021. He has contributed extensively in energy sector policy and regulatory activities over 25 years and has co-authored over 75 publications. He is a member of Institute of Engineering Technology, IIT London, a fellow of the Institution of Engineers Sri Lanka. He is also a senior member of the Institution of Electrical and Electronic Engineers, commonly known as IEEE. I now welcome Dr. Priyantha to provide a welcome speech for the webinar series.
Thank you. Thank you, Yash Kumar, for that very generous introduction. And let me start by welcoming all of you. Good morning and good afternoon and good evening to everyone, and wherever you are joining from. Welcome to the ADB webinar series on this disease resilient and energy efficient centralized air conditioning system. Today, we will have the first webinar on disease resilient and indoor air quality. I think it is a very important and a relevant topic in the current times, particularly during this pandemic. Let me give a little bit background on this technical assistance program under which this seminar is financed, and the webinar series itself spanning over a month. Air conditioning is becoming one of the most basic services in many cities of DMCs, where air conditioning can use for up to about 50% of energy consumption in public buildings. According to recent research, the novel coronavirus can survive in air for several hours. And as all of us know, Delta variant in particular can survive, and it spreads in air. Air filtration typically installed in standard centralized air conditioning systems are not effective in filtering viruses, as all of us know. Therefore, the recirculated air inside public buildings and other closed spaces can contribute to the spread of this coronavirus and bacteria, highlighting the important role air conditioning system plays in transmission of these diseases. Improper design, operation of centralized air conditioning systems can increase the risk of airborne transmission diseases like COVID, as we just said. In developing member countries, the risk of disease transmission through these systems is even higher due to the use of old air conditioning equipment, lack of regular maintenance, and overcrowding in closed spaces. Additionally, these air conditioning systems has a particularly the central ones, has a large GHG emission impact. In the current context, it is vital to design and operate disease-resilient, smart, green, and energy-efficient centralized air conditioning systems. The Asian Development Bank, in implementing knowledge and support technical assistance, regional support to build disease-resilient and energy-efficient centralized air conditioning systems to promote disease-resilient clean energy development in developing member countries of ADB. The TEA complements ADB's assistance programs to help its developing countries manage COVID pandemic and climate change mitigation programs. The TA team is assessing the energy efficiency and virus transmission risks of these centralized systems, making appropriate recommendations and piloting. These centralized systems in selected DMCs are being looked at during this TA activities. Until now, the project team has completed innovation challenge evaluation to identify and demonstrate technology solutions that provide disease-resilient and energy-efficient centralized air conditioning systems with smart grid digital systems in DMCs. The selected winner will receive innovation challenge grants up to $295,000 following successful completion of due diligence and negotiation of an ADB grant financing agreement. The final completion result will be announced in ADB Innovation Challenge platform within this week. And then we will negotiate with the proposal provider and sign grant agreement and seek no objection from the pilot project host country and disburse fund and implement pilot testing. This webinar series is one of the planned outputs of the TA program. This webinar series will share key strategies and minimize the risk of airborne transmission through the smart and energy efficient centralized air conditioning systems. The webinar series provides recommendations on how to mitigate the risks of virus transmission and ensure safe working conditions in public buildings. It will also share a brief overview of the market-ready technologies that can be implemented in the public buildings located in our developing member countries. I'm sure this webinar would be of great benefit and this knowledge sharing event will be of use to every one of you and hope you will enjoy it. Finally, let me wish the webinar series a success and thank you very much.
Thank you, Dr. Priyanka, for the welcome speech and for kickstarting the webinar series. Next on the agenda is a speech from Mr. Jinmiao Zhu. So let me introduce Mr. Zhu. Mr. Zhu is responsible for CCUS related work in Energy Sector Group of Sustainable Development and Climate Change Department, and process and administer regional technical assistance focusing on CCUS, low carbon energy technical roadmap, and advanced centralized air conditioning system. He received BS in environmental engineering from North China Electric Power University and MS in thermal engineering from Tsinghua University. Mr. Zhu is the project officer for TA 6563, this technical assistance program, which is supporting this webinar series on regional support to build disease resilient and energy efficient centralized air conditioning system that promotes clean energy development in developing member countries of ADB. Let me also acknowledge the support of our funding donors to ADB, the High Level Technology HLT, and the Clean Energy Fund CEF. I now welcome Mr. Zhu to provide us background and overview of this technical assistance program of ADB.
Thank you, Yash, for your kind introduction. Okay, I will share my screen. Yes, is that visible?
No, your screen is not visible. If you can enter in the full screen mode. Yes, I can see the screen. You can put it in the full screen
Is that
mode.
okay?
Yes, perfect. Thank you.
Okay, thank you very much. Good morning. good afternoon, good evening, everyone. I'm Jim Miao, project officer of the TA 6563. Welcome to join this webinar. I would like to take this opportunity to introduce this knowledge and support TA. Air conditioner is very common, and we can find centralized air conditioning system easily in office building, shopping mall, and hospital and other places. Air conditioning is one of the greatest inventions of the human. If there are no air conditioner in the hot summer, it would be very uncomfortable. With the economic development and urbanization, air conditioning has entered households and public buildings. In 2018, the global air conditioning volume has reached 1.75 billion units. In the future, the demand for air conditioning will increase significantly. China and India will have the largest demand. Air conditioning can bring the cool and comfortable living space, but its energy demand is huge. The energy consumption of the global space account for 8% of the total global energy consumption in 2019. If no action taken on air conditioning equipment and buildings, the share of the energy consumption will triple to 12% by 2070. Growing the electricity demand is equally reflected in rapidly rising CO2 emissions, which grew fivefold since 2000 to reach more than 250 million tons of CO2 in 2017. Now we are still suffering pandemic. We should keep social distance and no gathering due to COVID-19 crisis. The people working in office buildings also worry about the centralized air conditioning system will spread the virus or not. Under the COVID-19 pandemic, CAC system in public building is facing some new challenges, especially the risk of the various transmission. The poorly designed and the old equipment of the CAC cannot meet the hygiene requirements in many developing countries. High density of the people in public buildings will result in high risk of the various transmission and infection. Airborne transmission of the virus can occur in healthcare settings where specific medical producers called aerosol generating producers generate very small droplets called aerosols. At the early time, there was not yet universal acceptance of the airborne transmission of the COVID-19 virus. Now, some outbreak reports related to indoor crowded space have proved the possibility of the aerosol transmission combined with the droplet transmission. For example, in restaurants or in fitness classes, in many DMCs, such risk is higher because of inadequate hygiene standards, such as use the old and inefficient air conditioning equipment, lack of the regular maintenance, and large crowds in closed spaces. The violence and the capacity of the government institutions, as well as the operators of the public buildings, are also limited in dealing with these risks. Therefore, there is urgent need to build or retrofit various resilient and energy efficient CAC systems in the short and the long term. ADB proposed a knowledge support TA amounting to $1 million to help DMCs to cope with the new challenges in CAC system. This is the original TA and the gained knowledge from this TA will be shared with the DMCs and accelerate and speed up economic recovery and go back to normal life. The TA will assess the energy efficiency and the various transmission risks of the centralized air conditioning system in typical public buildings. Operational process for smart automated control system will be designed in different scenarios during pandemic, resuming work, and normal situations with the digital technologies. The pilot project will be procured through innovation challenge to demonstrate the benefits of the AI-enabled system, which address the efficiency and the health objectives at the same time. Capacity and the knowledge of the relevant government agencies and the public building operators on containing indoor various transmission will be enhanced. 3 pilots will be installed in public buildings of selected DMCs. The firm to implement the pilot system will be procured through innovation challenge. That is a competitive grant selection procedure. A selection of the DMC will be based on the pandemic situation, weather condition, and demand for the TA output. The final selection will draw on innovation challenge results. Pilot projects are essential to showcase innovative technologies and financial mechanisms that have the potential for scaling up through further government support or can attract private sector investment. Pilot projects undertake under the proposed TA should be replicable, scalable, and have a development impact and be sustainable. The high-level technology fund will provide grants to support a proposal from high-level technology providers selected by ADB evaluation committee. The 2-stage international competition followed by negotiations with the preferred proposers up to US $295,000 will be awarded to the best solution. We received 52 EOI submissions and selected top 5 EOIs. These top 5 applicants were invited to provide detailed proposal documents and give a presentation to introduce their technical solution and the pilot engineering plan. The finance pitching has completed last week, and now evaluation committee is processing selection approval, and the final results will be announced on the ADB Innovation Challenge webpage within this week. ADB will engage 8 individual consultants for a total of the 38 person months for international. Excuse me, please mute your mic. Thank you. For international consultants have been recruited and commenced the work. We will recruit 4 national individual consultants. The country will depend on the pilot project location. If you have interest on these positions, please follow up innovation challenge result announcements and the TOR advertisements in consultant management system of ADB. Training workshop, including online trainings and webinars, will be conducted for relevant government institutions, operators of the public buildings, and other public, private, and non-government organization stakeholders. The webinar series is an important output for this TA. Here is the schedule and contact points information. If you would like to share your knowledge, experience, or insight, please feel free to contact the session focus. You could be a speaker in next webinar. Look forward to hearing from you. Okay, that is all information I'd like to share with you. Let me stop here and over to you, Yash. Thank you.
Thank you, Jinmo, for giving an overview of the TA, Technical Assistance Programs of ADB. Next on the agenda, we have a health and indoor air quality expert, Richie Mittal, on this Technical Assistance Program. He is going to give a talk on disease-resilient indoor air quality in centralized air conditioning system. Let me introduce Richie Mittal. Richie Mittal is a director of Overdrive Engineering Private Limited. He completed graduation from BIT Mesra in 1983 and completed Master of Engineering from Delhi College of Engineering in 1984. He has more than 37 years of experience in this industry and has been a guest lecturer in many engineering colleges, including IITs. He serves at the various leadership positions in many societies, including ASHRAE, ISHRAE, and IAQA, as well as in many committees of national and international government organizations. I now welcome Mr. Richie Mittal to take over this session in managing the expert talks, as well as giving the talk on the overview of the work done under TA.
Thank you, Dr. Yash, for the opportunity, and thank you everyone for giving me this opportunity. I will just share my screen. Can you see me? And can you hear me? And can you see my screen, Dr. Yash? Dr. Yash, can you see me?
Yes, we can see you, we can hear you well, and we can see your screen.
Thank you. Perfect. Thank you, Dr. Yash. So I'll take this opportunity to thank Jinmo, Dr. Penita, and Dr. Yash for giving an opportunity to present here the presentation on disease resilience. So here we're going to talk quickly about indoor air quality. And then in indoor air quality, we talk about obviously thermal air comfort, because when we talk of indoor, so it's an enclosed area and we need to maintain a thermal comfort. We're going to talk about a little bit of indoor air pollutants, then particulate filtration, which I'm sure all of us know about it. We're going to talk about indoor air quality and health, because in this pandemic year, I think the air quality has gained a lot of importance. It was always important, but I would say that it has gained much more importance at this time, and people have started talking about it. We're going to identify the problems in indoor air quality and the methods to improve indoor air quality. So this is what I'm going to talk about quickly. So we know that in indoor aerosolization of infection is very important, and simultaneously, as I mentioned about thermal comfort. So in thermal comfort, relative humidity and temperature, there are two parameters. Obviously, ventilation plays a vital role, but still it makes an important part of it. So there are a lot of questions, and now I think it's been declared that this virus is airborne and it does spread through air. So ventilation and filtration being provided in air can reduce the airborne concentration, because there are a lot of myths about in indoor area. So I think there are strategies which I'm going to cover very quickly. But having said so, that air conditioning system can be run, but with various technologies to be used to filtration and adding fresh air. We have unconditioned spaces, but in unconditioned spaces there are thermal stress. So we need to take care of the thermal stress, and that is the reason why we are talking of enclosed area. Though the virus is not so affected in the open area because of the dilution of the air in that area. I'm sure this picture would have been seen by all of you very in a lot of webinars all over, is that while talking the viral load is less, while coughing it is higher, and while sneezing it is much higher. So this plays a very important picture which came last year, and it is being used by everybody at this time. This is one other picture which everybody again would have seen, is that, the thicker or the higher the diameter of the particle falls, the lighter one stays in the air. So that is what we really talk about. The droplets fall nearby spaces, and the lighter one, they travel much beyond. And that is why we have protocols which are being said that 6 feet distance, or for example 2 meter distance. But there are studies which say that in an enclosed air, this aerosol can travel up to 20 or 30 meters also. Talking on humidity, there is a chart which I'm sure everybody would have seen, that how effective, what is the best humidity level which has to be maintained. This is a Taylor chart which came up, and this talks about infectivity and survival of virus. So the range of 40 to 60% RH or 40 to 70% RH is normally being seen as the best range for less effective of a virus. It actually impacts the airborne transmission. It impacts the respiratory route also, in this. So with just to give an example, with a lower humidity, infected droplets come especially smaller than 0.5 micron, evaporates fast and become even smaller, remain suspended in air for a long time. Thus, the lower humidity, more such small infected particle would remain suspended. So you can imagine, the lower the humidity, the dry the air is, and the particles will float easily. When air is dry, it is more difficult to clean the surfaces. Again, we're talking of surface cleaning. So this plays an important role. So, coming back to this thermal comfort, 40 to 60% is normally being talked as, with the results, with the studies, that is the best RH to be maintained. Temperature again plays a very vital role, and temperature, they have been talking about 24 to 30 degrees centigrade temperature is a good temperature, depending on the various climatic, and higher go, the better it is. So there are also a lot of studies being done on this, and that is what is being recommended. So on the strategies part, what we would like to see is that, there are ASHRAE standards, and you will hear from the speakers from ASHRAE. We have ISHRAE standard, we have IEQ standard prepared by ISHRAE for good air quality. Then we can increase the filtration level in case of recirculation. As I mentioned, in any enclosed area, you have to increase the fresh air, or recirculation rates have to be increased. Add maximum fresh air. Now that's a very big question, how much fresh air, but it is always recommended. The ideal is 100%, but as far as possible, as much as possible is good for the system. Use of UVGI technologies at HU and ducts and upper, this is one other technology which has been used very frequently all over the world now. As I mentioned, maintain good thermal conditions, including RH, maintain social distance. As I mentioned, again, it plays a vital role. Wearing a mask, there are a lot of studies, but having said so, I think it is the most important thing, and it will continue for a long time. So there are a few strategies which, for safe environment, we talk about passive filtration. There could be a combination of filters where you can club in filters. There are studies which are happening with combination of particulate matter filter along with UVGI can give you a better result. Those studies are also available now. Then there are a lot of active technologies like ionization, ESP, PCO, PHI, and there's so many of them. I don't want to list them all, but I have a note which I would like to. The few of the active technologies are called as emerging technologies by WHO, and efficacy of these systems in real applications are yet to be established. But only thing that I would say, that one needs to be wary about using these technologies, about the byproduct and the efficacy. The recommendation that we are coming up with is that increase the ventilation rate like mechanical non-natural by adding 2 to 4 air changes of outdoor air. But this will call for a energy on that matter. Increase the filtration level. The filter rating of MERV 13 or above is always recommended. Temperature, again, it's a repeat of thermal comfort is important. Humidity also plays a vital role. As I mentioned, the lower the humidity, the challenge, and higher the humidity again is a challenge for mold and other things. Air distribution plays a very, very vital role. So you need to check the flow to reach out to all areas. Balancing of air again plays a very vital role for supply and exhaust, because there are a lot of applications where you may see that supply is there, exhaust is not there. So you need to balance. monitoring of indoor air quality again plays a very vital role, because till you see it, you don't know what is happening in this area. So with this, I will stop here and thank you for your time. And now I will move on. So I have next speaker, I have Mr. Donald Weeks. Welcome, Donald Weeks. I will quickly run through his bio. Mark, if you can just show the screen for Mr. Weeks. So just a quick brief. I know his bio is very big, but it's my pleasure to read. Mr. Weeks has 45 years of comprehensive consultation expertise and project experience in the implementation and management of inspection for hazardous materials in numerous buildings throughout Canada and United States, including university, colleges, government offices, and commercial residential buildings. During the course Mr. Weeks' career, he served in the numerous senior management positions in both consulting and insurance industries. He has also worked with numerous governmental entities at local, state, provincial, and federal levels. In his career, Mr. Weeks has provided expert guidance on all technical aspects of project involving occupational health and safety assessment, indoor air quality, asbestos, LEED IEQ, credit certification, LEED paint, mold, drinking water sampling. Now I would like to welcome Donald Weeks to talk about indoor air quality in the buildings. So over to you, Donald.
Thank you, Rich. I'm going to go ahead and share my screen here. Oh, I think it's still on Rich. So. Yeah. We need to make me a co-host.
You are actually, Don, you did try. Mark, can you help to make Don the co-host again? I think you were. You are co-host, John. You can share your screen.
Oh, there we go. Sorry.
No problem.
Apologize. So thank you very much, Richie, for that very nice introduction. And I'm going to present on indoor environmental quality in buildings. And I have gained another year of experience. Richie mentioned 45 years. I've actually now in my 46th year of doing this type of work. So I'm looking forward to continuing going forward on this. So my background is in industrial hygiene, which is different than indoor air quality. And I'll show the difference in the things that we talk about on this in this presentation. As it says there, this is a science and art industrial hygiene that is devoted to anticipation, recognition, evaluation, and control of environmental factors. So this is generally applied towards factories or manufacturing facilities rather than strictly office buildings or schools and things of that nature. And it is a well-recognized field of endeavor. It was first started in the early 20th century by a number of individuals, including Alice Hamilton, who worked diligently to get this particular field into the mainstream, and that would enable people to reduce the amount of sickness and impaired health that they were experiencing by working in some of these factories. So this has been around for a long period of time, and is what I've worked on and have a certification in. So this is different than indoor air quality. And indoor air quality is air quality within and around buildings and structures, and it's mainly a comfort issue, although it also affects the health and well-being of building occupants. This started about 40 years ago, back in the early 80s. For those of you who remember, there was at that point an energy crisis, and many buildings were affected by reduction in temperatures, reduced ventilation, and in some cases increased relative humidity and reduced airflow. And people worked in particularly office buildings, but also schools and public facilities and things of that nature, were complaining about the comfort that they were finding and were not getting in the buildings in which they worked. So indoor air quality, again, is a relatively well-established field and has been around for quite some time. But it is now superseded to some extent with the next one, which is indoor environmental quality. And this relates again to the health and well-being of those who occupy the space, but it also includes many other factors, including lighting, radiation, electromagnetic, ergonomics, noise, air quality is part of it, and damp conditions. This has been around about 20 years, since the beginning of the 21st century. And one of the organizations that I'm involved with, the Indoor Environmental Quality Global Alliance, which ISHRAE is a member of as well, has been looking at this particular area of expertise as we go forward into the 21st century. And it's definitely a part of what we're going to be looking at when we start to deal with problems with air conditioning in buildings, as well as with regards to changes in the way in which we work, specifically in terms of less buildings, large office buildings, and more working from smaller facilities, or in some cases working from home. How do we manage that indoor environmental quality for workers who are looking for that type of assistance from the people that they work for? So this is a growing area of concern, and there's many other individuals that are going to be involved in this: mechanical engineers, lighting experts, people dealing with radiation, ergonomics experts, noise experts, people who are going to be dealing with the industrial hygienists or with the indoor air quality specialists to deal with these new issues that are arising from buildings. So I'm going to go briefly through a couple of case studies so that people understand somewhat the differences between particularly indoor air quality and indoor environmental quality. This is a large governmental complex, 1.2 million square feet in Ottawa, Ontario. And there were a considerable number of complaints, periodic complaints about bad air, adverse health symptoms, including coughing, choking, other types of respiratory ailments of sorts. And the building had been subject to many indoor air quality surveys for many years. And they found no adverse findings when they did what I would call routine indoor air quality surveys. A routine survey of a building this size usually involves stopping at a particular location within the building for 5 to 10 minutes, running a series of tests for relative humidity, temperature, particulates, VOCs, and to look and see whether or not there's any differences in certain areas of the buildings. They weren't seeing very many dramatic differences, but when you're doing a building this size, you have to look at not only what is happening in the immediate space, but what's happening in other spaces which may affect the space that you're concerned about, and which may take place on a periodic basis, but is not a constant type of problem. But that wasn't something that previous surveys found. So we were called in to look at this building, and we focused in specifically on carbon dioxide and VOCs. And what we found was that by looking at certain areas in the building, particularly areas that face to the south, where the sunlight was coming through, we got elevated carbon dioxide temperatures or measurements in the afternoon, not necessarily in the morning and not necessarily after work, but in the afternoon, specifically when the sun was hitting the glass and people were working at their stations or their cubicles. There were elevated levels. And we talked to the building operators and managers, and we talked about what would be the appropriate approach to this particular problem. And one of it was increased airflow, obviously. And also we asked them to start monitoring the CO2 levels, which proved to be a very important aspect of dealing with indoor air quality in this building. With no measurements, we had no idea whether or not there were problems in a specific area at a given time. And there were certain areas that were going to experience different types of levels. You could be on one side of the building, the south side of the building, and experience problems, and you could walk to the north side of the building, maybe 100 to 200 yards down across the way, and you didn't feel the same effects. So there had to be some differentiation between the two, and you had to deal with what type of airflow you're going to have in the areas which are affected, and that was best measured by looking at the CO2 levels in those areas. So we also looked at elevated VOCs, and we found it in 4 locations. These locations, we then did a little bit more in looking and seeing what might be the results of that. And some of it had to do with personal hygiene products, but also there were chemicals used on indoor plants. And then the building was cleaned on a regular basis, usually once a week, if not more frequently. And these cleaning products that were used were also elevating the VOCs, the volatile organic compounds that were present in the building. These locations did have elevations of these levels, but there was no real health concern. But for people who were working that area, it was certainly noticeable, and it was irritating to some extent. So no long-term health concerns, but certainly not a pleasant place to work. So they needed to do, again, some ventilation changes in what they were doing, and also to talk to the individuals who were using the cleaning products and the chemicals for the indoor plants as to how much they used and how can they reduce that particular material so that it doesn't become airborne. Now I'm going to take a look at case study 2, which is indoor environmental quality. This is a building again in downtown Ottawa, Ontario, in Canada. And you can see that the design is for a sunroof in the building. This was facing again south, and the intent was to provide better lighting for the individuals who were working this area. And it did. It provided additional lighting, which was good. But unfortunately, because of the way in which the sunroof was faced, it also resulted in elevated temperatures. We're talking, typically in an office building in Ottawa, it's somewhere around about 22 to 25 degrees Celsius. We were measuring up to levels as high as 35 to 37 degrees Celsius. So this was a considerable increase in temperature. So what did they come up with? They came up with shades, polyvinyl chloride shades placed near the sunroof. Then to block the sun, particularly during the summer period when the sun was the most intense and the temperatures were the highest. The difficulty was they now had new complaints about a chemical odor in this area, and they couldn't figure out what the problem was. They talked to the manufacturer of the PVC shades, and he looked back and talked to the technicians and found that basically the ability of the shades were to withstand temperatures up to 140 degrees Fahrenheit, which it was an American manufacturer. So that's what we got as far as that. And of course, we were not seeing levels at the ground level that high. We were seeing levels that were, as I mentioned, down about 25 degrees Celsius. So, but this chemical odor was persistent, and we did some measurements and looked at what was on the side where the sunroof was, and what was on the side where there was no sunroof. Now you can see the shades on the windows. Now, when previous consultants came in, they did measurements to see if there were any type of problems in the building that they may have. Not measure. They wanted to measure and see if there was any indoor air quality problems that may be a problem, may be resulting in this chemical odor. Well, what they didn't do though is they didn't get off the floor, get on a ladder and climb up to where these shades were located. So we did that and went up and investigated that. And when we got by the window and between the window and the shade, we found that there were elevated temperatures above 140 degrees Fahrenheit, which resulted in off-gassing and odors. So what was the solution in this particular case? We replaced the PVC blinds with something that was not going to off-gas at that temperature. So you have to, in some cases, look beyond what is the immediate issue and take a look at what's going to be the long-term issue. And in this case, it was to replace the shades that were designed initially to prevent elevated temperatures, which resulted in elevated temperatures right at the window and where the blinds were, and that resulted in the off-gassing. So I wanted to connect this particular argument or this presentation to disease resilience. Now, I looked up a couple of definitions. What would be some of the problems with regards to disease resilience in IEQ? And as it says on the left, the resilience is a ability of people to cope with difficult, stressful, and traumatic situations. And they're trying to maintain or restore normal functioning. The higher the resistance, the lower the vulnerability and risk of illness. And psychologists define resilience as the process of people adapting well in face of the, as I mentioned there, a number of sources of stress, such as family relationships, but also serious health problems and workplace and financial stressors. And that's the role of resilience. So you can see what I'm highlighting is that you can't just look at the building itself. You have to look at the people who are in the building, because they're the ones who are going to be the ones who are going to have to do most of the resilience work. So let's take a look at some recent study. This is a recent Lancet COVID-19 commission designing infectious disease resilience in school buildings through improvements in ventilation and air cleaning, and it was just published last April. So you can see the quote there. It basically says that ventilation and air cleaning improvements are likely to lead to improved academic performance, in particular reading and math performance, and again, less missed school days, higher scores, and many benefits for teachers, including decreased respiratory symptoms, increased teacher retention, and improved morale. Now, this type of study was focused on schools, but many of the same types of findings, I'm sure, will be found when we deal with problems in office buildings through improvement in ventilation and air conditioning. We're going to see more resilience among the people who are working in that building. And that's through the improvements that we have to design in such a way that it doesn't just deal with the building itself, but with the people who are inside the building. Because why people are the most important asset in a building is really because the purpose of any building is to provide shelter and comfort to the occupants, and to provide an environment where occupants can work, live, and play successfully, and particularly here in Canada and in other places in the world, to be able to withstand extreme weather and atmospheric conditions while protecting the workers, and to provide for the mental and physical well-being of the occupants. If we focus in on the people as being the most important asset in the building, then indoor environmental quality becomes a real issue that we need to address while we're increasing our ventilation, while we're building up the resiliency of the building itself. So in conclusion, what I would like to say is that indoor air quality, indoor environmental quality is a complex, multidisciplinary subject involving both health and comfort issues. And we need to look at the key improvements in buildings on the basis of indoor air quality, as far as the knowledge of the building's heating, ventilation, air conditioning systems, as well as work closely with mechanical engineers, building scientists, building operators, and the people who have to work and live in these buildings, so that they get a say as to how the building is going to operate, because they're in there 8 hours a day, or in some cases 24 hours a day, depending on the circumstances. And they know more about the knowledge of the air contaminants that are in there than we do. We may come in a one-day basis or even a week-long basis to look at it, but they will be able to tell us more specifically what kind of problems really exist in the building. And then one of the key things that I always emphasize is you got to have good communication skills. You have to be able to talk to people, ask them questions. You have to be able to understand what it is that they're concerned about, and try to really deal with what their issues are, so that they feel like they're being heard. So with that, that's my contact information, and I appreciate the opportunity to be able to talk to you today. And I wish you the best for the continuation of the webinar series over the next couple of weeks. Thank you.
Thank you, Don, for good insight. I know the time is tight for all of us. I know you can go for hours, but we have a time limitation. So thank you, Don, for being with us. So next I go to Bill, and I'm going to read his bio, which is very interesting. And so thank you, Bill, for being here. So just a quick introduction. Dr. William Bamford is a professor of architectural engineering at the Pennsylvania State University. He holds BS, MS, and PhD degrees in mechanical engineering from University of Illinois, and is a registered professional engineer. He's the author of co-author of more than 170 technical papers and articles and 14 books and book chapters. Dr. Banford is a fellow of ASHRAE, American Society of Mechanical Engineers, ASME, and International Society of Indoor Air Quality and Climate, ISAC. He served as the president of ASHRAE in 2013-14 and currently chairs its epidemic task force, which is being, I'm sure all of us would have heard him at a lot of places. And thank you, Bill, for all the great work. He's also a recipient of Penn State University Engineering Alumni Society, World Class Engineering Faculty Award, and a Penn State Exemplary Designation for Faculty Outreach. I would now like to welcome Mr. William Balfin to speak about indoor air quality, health, and control technology with active and passive. Over to you, Bill.
Okay, thank you very much, Richie, for the introduction. I think my slides are showing, and I have too many and time is short, so I will move right into my talk. I was asked to speak to the topic of indoor air quality, health, and control technologies, and that's a lot to cover in 15 minutes. We'll see what I can do.
Thank you, Bill. I mean, you are audible, you are visible, everything is good. Go ahead.
Great. So what is indoor air quality is probably a good place to start. Don Weeks showed this definition, which comes from the United States Environmental Protection Agency. And I show it really to indicate that despite a long time that we've been researching indoor air quality, we still have a hard time saying exactly what it is when we get to the quality part. So what the EPA says essentially is that indoor air quality is the quality of air indoors. This word quality is really elusive, and I think it clearly relates to levels of indoor air contaminants and the consequences of exposure, but it's actually quite subjective what we consider to be acceptable. And there really isn't a consensus definition of what would be ideal air quality today. In standards like ASHRAE Standard 62.1, which is the code basis for building codes in the United States, we find a working definition of acceptable indoor air quality that I would say describes air that's safe and satisfactory. So the intent is to have no known contaminants at harmful concentrations, and also to have air quality that to most of the occupants is acceptable from the point of view of odor. And this is usually achieved prescriptively through ventilation and specifying minimum filter efficiencies. We could also discuss the definition of the term health, and as Don Weeks indicated, there are multiple definitions here as well. I found a really interesting article that discusses this and proposed three different current definitions of health. One is the absence of disease or impairment, which is essentially a medical definition that to the extent that there's disease, there isn't health. That's somewhat limited. Another proposed definition is that it's a state that allows the individual to cope with demands of daily life. That's subjective and exclusive. It essentially would say that some people can't be healthy and some people may not be healthy, but not realize that they are. They may have disease that doesn't really affect their daily life, at least at the current moment. And the third definition is one that describes a state of balance, and this is moving in the direction of definitions of well-being that are much discussed today. So when we try to control indoor air quality, what do we do? Well, we're mostly dealing with these exposures that lead to disease. And World Health Organization, among others, has tried to address some of the exposures that could lead to disease. They have said in the preface to one of their air quality guidelines that clean air is considered to be a basic requirement for human health and well-being. So in the three documents shown here that were issued over the last 20 years, we find both indoor and outdoor air quality criteria, but really still for a small subset of the things that we might be exposed to indoors. And this really only scratches the surface of exposures, and also does not deal with airborne infectious diseases, which in general have been omitted from our air quality standards. ASHRAE is also working in this area, and there's an addendum to ASHRAE standard 62.1 that would replace the indoor air quality procedure as it's existed in the past, that proposes a list of design compounds and particulate matter, all of the things shown here. So these are fairly common indoor contaminants, and the new indoor air quality procedure, instead of requiring a specific amount of ventilation, would require control of all of these contaminants to at or below the design limits shown. So we are moving at least in the direction of performance-based ventilation that relates to the definition that I showed previously, but it's still simply safety and satisfaction that is being targeted here. And a key question today is, can we go beyond health? Decades of research have shown that if we go past our minimum standards, in some cases substantially, that we could see benefits of productivity, cognitive function, student learning, sleep quality, consequences of infectious diseases, and others. And it's also been shown conclusively that there are large monetizable benefits of doing this that should drive policy change, which Lydia will talk about. But in general, these benefits have mainly wound up being overlooked externalities while we focused on other also important things like energy and the environment. But it's time to put all of these things on an equal footing. And we often hear people say, well, we want better indoor air quality, but it has to be sustainable. And what I like to remind them is that health and well-being, which come from indoor environmental quality, are among the sustainability goals of the United Nations. So what we're really looking for here is, I think, balance, not emphasizing one to the exclusion or detriment of the others. So now engineering controls, which was what I was really supposed to talk about here. These are part of the hierarchy of risk mitigation measures that are specifically intended to reduce exposures by either removing contaminants from the air or by directing them away from people. And controls need to deal with all the different classes of indoor contaminants, particles and aerosols, gases and microorganisms. There are lots of specific technologies that deal with one contaminant type or another, and there are some that are general. And so we have choices to make about how we're going to approach achieving whatever our definition of indoor air quality is. And ventilation is considered to be fundamental because it's the easiest control we can apply. Just by making openings in a building, we can have ventilation. So the purpose is to dilute or displace contaminated air. We can do that with mechanical systems. We can do that with natural ventilation and also with hybrid systems. It's generally required for all occupied buildings because it addresses all types of contaminants to some extent. The rates that have been specified over time have varied wildly. I've shown the figure on the right, the history of ventilation rates going back to the early 1800s, and we can see that they've been up and down, 30 cubic feet per minute per person for infection control, and 15 CFM per person for odor control, and 5 CFM per person for energy conservation. We found out that didn't work very well. We're not at the health effects, or I should say the disease control level right now, but we're somewhere at the odor control level, which doesn't do a lot for infectious disease transmission risk mitigation. This is something that can be very expensive if we go to high levels because all of that outdoor air has to be conditioned to indoor conditions. But we've seen from a large body of research that there are benefits for health and productivity. sick building syndrome symptom incidence reduction and task work performance improvements, for example. So it can be a good control if it's not energy intensive. Air distribution is also important. So the type of air distribution that we use, whether it's mixing ventilation, which is very common, or stratified distribution, which is becoming more common, that makes a difference in terms of how much outdoor air we need for ventilation and how effectively it removes contaminants. So this is something that can make better use of the outdoor air that we bring in and help us to achieve our goals as far as energy are concerned. Mechanical filtration is what we rely on primarily for removing particles from the air. Most buildings have what I would call moderate levels of filtration. The original reason for putting filters in air conditioning systems was to prevent fouling of wetted components like cooling coils, but to protect health, we need a higher standard than we find in minimum standards like ASHRAE standard 62.1. So the filter grade is important for a couple of reasons. One of them is that small health effects sized particles that can reach the alveolar region of the lungs will easily penetrate a typical minimum efficiency filter like a MERV 8, as you can see in the figure on the upper left, which shows the ICRP deposition profiles. So most of the particles that are handled by the minimum filters are in rating classes 2 and 3 for ASHRAE standard 52.2, and the ones that get into the alveolar region have no minimum requirement. Same thing for respiratory aerosols that may be infectious. The bulk of the infectious load, the viral load, is in particles that are not well controlled by minimum efficiency filters, which is why ASHRAE has been recommending filter upgrades throughout the pandemic to the level of MERV 13 at least. And again, we know that if we would upgrade indoor air quality by improving particulate filtration, there would be lots of benefits from that in terms of people's health, and also the cost of healthcare is shown in this work by Montgomery et al. That has estimated the annual morbidity and mortality benefits from using different MERV-rated filters in various environments where the outdoor air quality profile is widely varying. The worse the outdoor air, the better the health benefits. And during the pandemic, we've seen that filtration can, if we're looking at control of infectious aerosols, be a more energy efficient and cost-effective method of control than increasing ventilation. And then we come to air cleaners. There are a lot of choices and a lot of questions about them. ASHRAE and others believe that for control of infectious aerosols, ultraviolet germicidal irradiation is the only technology that's really well proven, especially using 254 nanometer UVC with produced by mercury vapor lamps, which we've done for a long time. For gases, sorbent technology is still the preferred method. Even though it has its limitations as well and its complications in application, but sorbents have applied for a long time to remove gases and have the benefit of generally not causing other problems. But this leaves what Richie called the active air cleaners, what I would call the reactive species air cleaners or the additive air cleaners. And this is a whole class of air cleaners that put things into the air. They add chemicals to the air in order to try to do something worthwhile. They claim to target both gases and particles and actually microorganisms as well. This includes things like photocatalytic oxidation that creates hydroxyls and dry hydrogen peroxide, which puts low levels of hydrogen peroxide gas into the air, and bipolar ionization. As the two title pages of papers on the right indicate, there's research going on right now that in some cases questions the efficacy of these technologies, and in others suggest that maybe there are health effects from the use of them that need to be considered. The germicidal UV can be used in a wide range of facilities. It doesn't have to have an HVAC system to be installed in, and in fact, the most effective way of using it is an upper air system where we put the fixtures directly in the occupied space, which can achieve a very high equivalent air change effect for controlling pathogens in the air. And Don Weeks mentioned humidity and temperature. I'll mention it briefly that something we've looked at closely in the course of the pandemic is this really an important control. And while there are certainly benefits to humidification and dehumidification in buildings to stay within a reasonable range, it's something that we don't feel is as effective as other controls for COVID specifically. And there's a lot of data that suggests that, like the work of Lindsay Marr here on the right, that shows that although there's a big range of inactivation as relative humidity changes, the overall impact of it on removal of viruses from the air is relatively minor. Yet ASHRAE for a long time has recommended humidification in a 30 or 40 to 60% range because it is beneficial in a number of ways. So to end here, my takeaways, good indoor air quality has many definitions. So the definition we choose is a really important one. There's a very strong case for the impact of indoor air quality on our health and well-being. We really ought to move forward and act on that. There are lots of technologies that exist to help us control air contaminants. We don't need a lot of new ones, although some of the new ones may help. There are promising technologies that need to be further investigated to develop standards to determine whether they're actually safe and effective. And if those actually work, then they can be a big piece of this solution to balancing indoor air quality and energy use and emissions of buildings. So that's the challenge in the end, is to combine the tools that we have available to achieve a high level of indoor air quality, but without compromising these other goals. And with that, I'll conclude, and don't think I've run over too much. Thank you.
Thank you, Bill. Thank you for a great insight, and I really love hearing you, and I'm sure all of us would have loved hearing you for a longer time, but we have a tight schedule on the time. So with this, thank you very much. I go to my next speaker. I would like to introduce Lydia Moroska. She's a distinguished professor. One second, can you display the, thank you. Thank you. So I'm going to read a quick one about her. She's a distinguished professor at the Queensland University of Technology in Brisbane, Australia, and the director of the International Laboratory for Air Quality and Health at CUTE, which is a collaborating center of the World Health Organization on research and training in the field of air quality and health. She is a physicist and received her doctorate at the Jagiellonian University, Krakow, Poland, for research on radon and its progeny. An author of over 800 journal papers, book chapters, and referred conference papers, Lydia has been involved at the executive level with a number of relevant international and national professional bodies. She's a member of Australian Academy of Sciences and a recipient of numerous scientific awards. I would like now to welcome Professor Lydia to speak about indoor air quality, a regulatory no man's land, how to change this. Over to you, Lydia. Thank you.
Thank you very much, Richie, for introducing me, and thank you for inviting me to give this presentation. I'd say Bill's presentation was a very good introduction to my presentation. The final points he made about the technologies. We have amazing technologies available. We've got also amazing science on indoor air quality available. I've worked in this field for quite a long time. So all is in place, but there's one obstacle. If there's no right regulatory framework to accept these technologies or science, or even more to mandate this, nothing really will happen, because no new technologies or no technologies which cost even a little bit more than without using these technologies will be used if they are not mandated, because the building developers or whoever are on the initial point of the process will have no interest in increasing the cost because they are not the ones who will be paying for the healthcare cost and other costs as Bill outlined. So that's has the title of my presentation. I'll start to sort of put a comparison between indoor and outdoor air. I start with management of outdoor air to get you understanding how it works. So as Bill already mentioned, we've got WHO air quality guidelines, and they serve as the basis for national standards. And national standards are enacted based on the health effects of pollutants. So this is the basis for developing of the WHO guidelines and the economic impacts of controlling them. So there are countries in which levels of national standards are higher than those of the WHO because of the economic considerations. As is, most countries around the world have outdoor air quality regulations. Now, in terms of management of indoor air, the situation is very different. So starting with what WHO has in place for this, Bill already mentioned the documents which are in place. So in particular, the guidelines for selected pollutants, and this is the list of the pollutants included in this document. I'm not going to go through the specific pollutants. Now, the second one is dampness and mold, but the issue here is that the guidelines are not quantitative, unlike the guidelines for selected pollutants, but qualitative. So basically, the conclusion is there that creating the situation of dampness results in development of mold. But I was part in the process of developing these guidelines as well as the selected pollutants guidelines. And basically it was not possible to come to agreement on any quantitative values. And there is a document also on household fuel combustion. And here we are talking mainly on situation when open fires or solid fuels are used. Now you may ask, what about particulate matter? Because particulate matter is not on the list of the selected pollutants. So where is it? Well, it is as a part of the WHO air quality guidelines, which we considered outdoor air quality guidelines. So the consideration was that the values which are in outdoor air quality guidelines are the same. Will be used for indoor air quality guidelines. By the way, the WHO air quality guidelines are being updated. I'm a co-chair of this activity, and the guidelines are new guidelines are at the point of being announced very, very soon. So this is management of indoor air quality, but as you can see, there are many different documents. So if one wants to get to the bottom of what is specific about a particular pollutant, needs to search through different documents. Now, the situation gets much more complicated when it gets to management of indoor air quality from the point of national standards. So most countries do not have any indoor air quality standards. There is no directive guidelines, for example, or standard at the European level at all. You may be surprised by this. Less than 20 countries around the world have national indoor air quality standards or guidelines or even plans to put them in place. Only several European and Asian countries have promulgated national indoor air quality standards or health guidelines. None include airborne pathogens. And in many cases, the threshold values are higher than the current WHO guideline levels. Now, you may ask, so in most countries that have indoor air quality standards, there are no enforcement procedures. I was going to say, you may ask, how do I know all of this? Because I've co-authored a chapter for this particular handbook of indoor air quality, which is in preparation and will be published quite soon. So it's quite amazing, really, that compared to outdoor air quality, indoor air quality from the regulatory point of view is really so underdeveloped. What are the factors contributing to limited progress in managing indoor air quality? Because it could, many would ask a question, well, outdoor air quality is maintained so well, what about why it's not indoor air quality? So globally, this is just a very complex situation, a complex political situation, complex social and legislative situation regarding indoor air quality, lack of any open, systematic or harmonized approach, full stop. I'll give an example from the Australian angle, because that's what I understand the best. And some of these points apply to other countries, and some of the points are different. So basically, depending on which country you are, you can kind of associate with some of this, but not with the others. So first of all, in Australia, there's no single national government authority with a responsibility for indoor air quality, specifically indoor air quality. Now, environmental legislation as well as health legislations are at the discretion of individual states, not the Commonwealth. So again, this is distributed and not uniform across the country. In individual states, there are no bodies directly responsible for indoor air quality. Responsibilities are spread between different organizations. So for example, schools are within the Department of Education, of course, healthcare facilities, Department of Health, and so on. We can go different buildings, different facilities, depend to different areas, different ministries. Now, there are no performance standards for indoor environment, only design and operational standards. Bill already mentioned this. So this is the beginning of the list of the problems. Now the list continues. Occupational and residential environmental indoor environment standards are treated differently. There's lack of funding for indoor environment evaluations and research for that matter. Basically, it was extremely difficult over the years and decades to get any support for indoor air quality research. Information on assessment of indoor environment is often available only to building owners and treated as confidential, and in interdisciplinary professional bodies that have a focus on indoor air and more general approach struggle in competition with professional bodies that are more narrowly oriented. Now, again, you may ask, how do I know this? Did I do a recent research on this? Well, if you see the publication, these are proceedings of the Healthy Buildings Conference in Finland, 2000, 20 years ago. And basically, nothing has changed over this 20 years. The situation is exactly the same, which I was acutely made aware again during the pandemic, when it's been basically impossible to move any actions on indoor environment, specifically ventilation, at all so far. So the issue of performance, excuse me, performance versus design or operational standards, which Bill already mentioned. Outdoor air legislation is based on performance standard, which means concentration levels of pollutants are considered and included in the legislation. However, indoor environment legislation has its roots in the design and maintenance standards. So what are these? For example, factors including air exchange rate, filter specification, or material emission rates, which is all good and all important. However, each of them is directly related or contributes to indoor air quality or indoor air pollution, but it's not the only one responsible for this. So there's no overall checking of the performance. Now, in relation to ventilation standards, Bill already talked about ASHRAE standards. They are also in Europe REBA standards. However, none of them explicitly considers health or infection control. Now, considers in what sense? In their statements of purpose and definitions, which is essential. So this is really absolutely the key. If the national documents like in Australia, national building codes, don't include this statement that the document is for the purpose of controlling health, including infection control, nothing is going to happen about this, full stop. WHO has recently developed this road map of ventilation in the context of COVID, which is good. However, it doesn't directly address airborne transmission, so it's not clearly stated why ventilation is important. And therefore, national authorities don't really take it as seriously as they would if it was stated there. So mitigation of indoor and environmental hazards. Well, we talk a lot about mitigation of indoor airborne infection during this presentation and over the last year and a half. But of course, there is also all the sources operating indoors and generating pollution, which must be controlled. There's prevention of ingress of outdoor air pollutants. I noticed on the chat there was a question how to run the system if outdoor air pollution is considerable, like these bushfires here. There's the thermal comfort, which we've discussed. If we enclose buildings too much dampness and then mold can develop. So unless all these things are taken into consideration at the stage of building design, HVAC system design in terms of building operation and crucially considered energy demand, it's very difficult to do anything later. And if this is not mandated, nothing will be done at the building design stage. So in the future, what to do? So as I've described, at the moment, there's no one whose role is to oversee management and control of indoor air quality to protect human health and the environment. So is this pointing fingers, who is the one who should do something and no one does? How to change this? Well, the only way is to start from the top. And by starting from the top, I mean having these important statements at the beginning of the most important documents, national documents, which mandate design of the building systems. There's a long way to go before this really happens. So with this, I'll thank you for your attention.
Thank you, Professor Lydia. So nice to see your thoughts, and I think you talk the reality, which is a ground reality.
Yeah, the reality.
I know. Thank you. I think all of us know about it, but we don't talk about it. So you're the one who's talking about it. So thank you very much. With this, we have the last person as Dr. Yash Shukla, who's going to talk about, who's going to take over the question answer. So I just quickly run through a brief intro to Dr. Yash. Can I have the slide, Mark, if it's possible, for Dr. Yash? Till then, so thank you, Mark. So Dr. Yash Shukla is Executive Director at Center for Advanced Research in Building Science and Energy at CEPT University in India. He has more than 15 years of international experience in building energy efficiency research and serves as a lead on several groundbreaking energy efficiency research projects at CAPSE. He currently serves as a team lead of the Technical Assistance TA 6563 program by the Asian Development Bank. I would now like to welcome Dr. Shukla to manage the question answer session and the closing section of the webinar. Over to you, Dr. Yash.
Thank you, Richie. Thank you for organizing this wonderful session. I have received 3 questions so far. So before I start asking the question to expert speakers, I would request all participants to please post your questions in the chat box. And utilize the time and the expertise, and we can ask as many questions as possible within the time. We have about 10 minutes for question and answer session. So I will take, we have so far received a few questions. I'll start with the first one. The first question is on the ionizers. So I will direct that to Bill. You being, I'm pretty sure this question has been asked you many times over the last couple of years. So if you can give your opinion about the ionizers, which are available in the market. Bill, over to you.
What is the question about them?
The question is that the opinion about the ionizers and their functioning and their suitability.
Yeah, well, I mean, there's certainly demonstration that ionizers can cause agglomeration of particles and result in reduction in airborne particulate levels. In fact, Lydia's group has done some of that research. I think the questions though during the pandemic have been, is it really effective for reducing airborne pathogen levels, and are there byproducts that are produced? And I think the main finding of some of the recent research has been that the effectiveness has not been as good as hoped for, or perhaps claimed, and then there is some production of potentially harmful byproducts, although I haven't seen studies that indicated that it was at levels that would be of concern. But in general, we don't want to be adding chemicals to the air that are toxic if we don't need to do it. So and also there are no real standards for evaluating these in application realistic situations. So for a number of reasons, I think it needs to continue to be studied and standards need to be developed. And that's actually something that ASHRAE is starting to work on. It'll take a while, as you know, the standards process can be long.
Absolutely. So thank you. Thank you for raising that. Still an emerging technology that needs to be evaluated and be very carefully used in the building. So there is a relevant question, a pertinent question. So I'll club that with the same for you, Bill. It was on the UVGI. Question is from Mr. Sharma saying that, is UVGI a proven technology or still experimental? We have the experts here. Please let us know and how effective it is, whether it's effective in retrofitting in AHU with lamps or installing the lamps in upper air areas. So if you, I know you talked a little bit about in your presentation, but if you can elaborate a bit.
Well, sure. To the first question, UV was first applied for air disinfection in the 1930s and was very effective against childhood diseases in schools in the US and the Philadelphia area. A very well studied and accepted technology, and the Centers for Disease Control in the US includes it in its tuberculosis control guidelines, and it's used extensively in healthcare facilities. So I think there's no question that it's a well-developed technology that's effective. There are questions, though, that haven't been answered about UV photochemistry. So, again, there's something where we've been using this technology for nearly a century, but hasn't been much attention to what does it do when it interacts with indoor air and surfaces. As far as what's the most effective application, I think no question that the most effective is upper room, because that can produce 10, 20, even 50 air changes per hour equivalent in some cases, depending on airflow conditions and on what the pathogen is, but it has to be applied space by space, so it can be more expensive. Air handling unit installations can also be effective, but keep in mind that you're limited to a clean air delivery rate that's equal to whatever the system is providing, and you probably have a filter in series with it. So if you have a high efficiency filter that's removing, say, 85% of the particles that may contain infectious aerosol, and you put in a 99% efficient UV system downstream of it, you're getting 99% of 15%. So its effectiveness isn't very high. And that said, though, it's a less expensive way to treat a large area in a building if you have a central air distribution system that recirculates.
Thank you, Bill. So then I'll ask the next question to Dawn. This question, I think, is asked by Mr. Zizan Ahmed. If the question is that if outdoor air is polluted during daytime, which strategy should be followed, I guess, to maintain ventilation and better indoor air quality. if you can, it's a very vague question, but if you can answer it in a minute or two to give an overview to the participants.
Yeah, I'm looking at the mechanical engineer bill right now on some of this, but what I would say from an industrial hygienist viewpoint, obviously, we want to keep the polluted air from entering into the building. The best way is to do it through filtration and elimination if we can. The big difficulty I find with outdoor pollution and as it affects indoor levels is that we end up with whatever we get from the outdoors staying longer in the indoors because there's not as much airflow as there would be outdoors. So we're actually in some cases measuring higher levels indoors of certain contaminants than we do outdoors, simply because it's been sort of a stabilized type of environment. But yeah, filtration is the key, and I'm going to pass it to Bill if you want to add anything to that at this point.
What was the question again, Yash? I kind of lost track of it while Don was answering.
Yeah, so the question is, if the outdoor air quality is bad, what are the different strategies that can be used? And I'll just club it to a recent question that we got. It's saying, the filtration is the foundation of any air system. So Mr. Chopra is asking that people tend to wash these. Please suggest over it how these can be sort of eliminated. So it's sort of asking the use of filtration and active and passive sort of technology.
Well, filtration of outdoor air is something that's just going to be necessary if we're going to keep relying on it. That's why I hope that we can make air cleaners a bigger part of our air quality control systems, because in urban areas for the foreseeable future, we're going to have problems with ozone and with various automotive emissions and particulate matter as well as gases. So I think a strategy of treating outdoor air as necessary is important. If you look at ASHRAE standard 62.1, if you exceed the requirements or the national criteria for PM10 or PM2.5, then additional particulate filtration is required. And if you exceed the ozone limit, then treatment is required for that as well. And I think we just may have to add more air treatment systems to outdoor air if we're going to have to rely on that. So I think not making large increases in outdoor air and trying to figure out what is in indoor air that needs to be controlled well enough that we can use active controls that are specific to different kinds of contaminants is probably the best strategy, and that's a work in progress.
Thank you, Bill. Thank you, Don. So now we have time for one more question. So I'll direct this question to you, Lydia. This is a question where if you can brief us a little bit about the new WHO standard, I think that would be very helpful for the participants.
Well, I wish I could, but I can't because they have not been announced yet. As I said, it's coming very, very soon. Hopefully, if things go well in September. And I would be very happy to give a presentation in the forthcoming webinars. But at this point, I can't say anything about this yet because
Absolutely.
the guidelines haven't been announced yet, but it's a very exciting moment for me once they are announced because we worked on this document for several years. It's such an important document, so I'll be very, very pleased when it's out and available. Great. But not yet.
Thank you, Lydia. So we look forward to we'll closely look for the announcement pretty soon and closely follow and hopefully organize a presentation about the same in future once it's announced. So with that, I think we have a very limited time, so I would just move to the last portion of the webinar. Thank you again to Don, Bill, and Lydia for taking their time for the presentations and for all the expert speakers. With that, we will, I wanted to talk about the last series of webinars. So this is a webinar series as explained by Jin Miao, and that we have 4 webinar series planned in the future. So I just want you to let you know the dates. Please block your calendars on next Wednesday and the 3 Wednesdays after that. So the next webinar on this series will be on energy efficient centralized air conditioning systems. The third webinar will focus on smart centralized air conditioning systems, how control systems can be used for disease resilient and to achieve energy efficiency in centralized air conditioning systems. And the last 2 webinars will focus on few of the innovation technologies that we have been looking around in the competition, as well as on the refrigeration management. So overall, please, there will be very, very interesting webinars, and I request all of you to block your calendar. It will be there at the same time in the next 4 Wednesdays. Thank you very much. With that, I'll just thank again all the speakers, Richie for organizing, and Jin Miao for the all the work that has been done for the technical assistance program. And with that, I end the webinar. Thank you, everyone. Thank you, participants. You will receive the feedback form for this webinar in particular, and each webinar after. I request you to please submit the feedback form so we can learn from it and we can improvise the webinar series. Thank you.
Thank you.
Thank you.
Bye.
Thank you. Thank you, Bill. Thank you, John.